Hello, my name is Taylor B, and I'm going to be introducing our progress report for FEA analysis ME404. So this project is going to be going over our sprinkler system that we're going to be doing analysis on. And my team's members are myself, Taylor B, Cole Tinsley, and Joseph Lentz. So to go back and introduce our project, or I guess kind of remind people about our project, we're doing a sprinkler system. So the idea and the inspiration behind this is from the Palisades fire down in California. Really, we just want to try to go through and see if we can optimize a spray pattern for a sprinkler system. Uh, kind of realize though is that that is a fairly advanced, a pretty complex thing to do, especially their limited experience with FEA and its modules. So especially since we don't have a lot of experience with ANSYS Fluent, which is where we could do the CFD, we're really going to be focusing and kind of modifying our project to focus on the stress analysis in the mechanism of our sprinkler system.
Hi, I'm Cole Tinsley, and I'll be going over the preliminary calculations for the load that's against our deflector and will be causing the stress that we'll be analyzing. The fluid force formula is very simple. It's just the mass flow rate times the velocity of the fluid. And the mass flow rate equation is, again, very simple. The issue with calculating this was that I needed to find the velocity of the fluid given the pressure behind it and the areas. So I needed to have Bernoulli's equation and the continuity equation in order to get that velocity at the end. With the velocity at the end being 52.64 inches per second and the mass flow rate being 0.0336 pounds per second, we were able to get a continuous force calculation. The parameters on the right side there were partially estimated in some internet sourcing, just kind of grabbing at this and that. So estimates are subject to change for that water pressure. It's kind of 50 psi was a residential pressure. Might need to change that later, and the diameter of the pipe and the aperture, which is the exit uh, area, can also be subject to change. Down on the right, we have a example of where that continuity equation, for those of us that have taken fluids, it's very, we've seen this a bunch of times. For those that haven't finished fluids yet, you're going to be seeing a lot of this. It's pretty simple, so it's not too bad to understand. Bernoulli's being simplified the way it is because, at the exit, we don't have an exit. We don't have a pressure like in air. Well, we do, but it's air pressure, and, that's accounted for. There's no change of height either, so those PGH points are subtracted as well. Next slide. Next slide. There it is. Okay, I'm going to be introducing the stresses on the deflector that we've identified, and I think Joseph is going to be talking about it more in detail, but the axial stress is kind of between the fluid coming down and the pin holding up on that stress on that deflector. So the pin from that 3D model, you can see there's a hole for that pin, and it would be fluid coming down and pressure coming up, and it would form an axial force, an axial stress. The bending is kind of more obscure to understand. You have the fluid comes down and then it kind of spreads, and even coming down, it's not a pin, it's a stream. So you would have forces that are a little bit outside of the center, and you would have the singular central force coming up, which would create a slight bending stress on the entire deflector. Think about if it were a piece of paper, it would come down and then it would kind of spread over the pin coming up. So yeah, we're not sure if we're going to be able to get a bending stress formulated with FEA, but the axial should be pretty quick and simple to understand.
Hello, I will be going over the formulation used in the analysis for this part. We used the direct formulation. We will be doing everything symbolically because we have not finalized the material and the shape of the part. We will find an equation for deformation and use that to solve for strain and stress symbolically. The deflector will be simplified into a spring between two nodes. Node 1 is pinned, and so there will not be any deformation at node 1. And node 2 is where our load is applied. The load is from the stream of water on the deflector. As mentioned previously, the stream of water will be distributed over the deflector, which will cause bending stress. For the direct formulation, we will be treating the stream as a resultant force, a compressive axial force on the deflector, and we will be ignoring any bending stress to make the calculation simpler. We will also be ignoring any of the teeth shown in the 3D model because that would add more to this analysis that we don't necessarily know yet. But if we were to add those teeth, it would be as simple as adding more springs and more nodes. The picture shown on this slide is a good representation of the analysis we're doing, except the force is compressive and not tensile, and node 1 is pinned and not fixed. With this model in mind, the stress and strain can be solved for. We start by finding the spring constant, which we pull from example 1.1 in the textbook, which gives us K equal to EA over L. We can then plug this into the force in the spring equation to find F equal to EA over L times U, which is deformation. It's also worth mentioning that E is the modulus of elasticity, A is the cross-sectional area of the deflector, and L is the length across it. We can then solve the force in the spring equation for U, finding that U is equal to FL over AE. In the post-processing phase, we can use our deformation to find strain, and then use that strain to find the stress. This equation can be used for any other elements that we decide to add, and it is a decent approximation of the stress and strain and deformation in the deflector. There are some improvements that can be made. As mentioned earlier, the load was greatly simplified for analysis. A better model would consider the bending stress. Additionally, the water from the pipe would hit any teeth that we may add to the deflector later on, which would create a force that's perpendicular to the axial force in this model. Moving forward, it would be good to use FEA methods in 2D and 3D, as well as any FEA methods for fluid dynamics for the water. For now, the direct formulation is good enough to model this.
Thank you for watching. If you guys have any questions, be sure to let us know. Thank you. Bye.